Let me first of all bring up the syllabus. As you can see, I've updated it with the lectures. And notice the Chapter 9 assignment is still there. I mean, it is there, so you can start on it anytime you want. In terms of Chapter 8, it's due today, but if you're a little late, I'm not going to worry about it. Again, but I definitely want it by Friday. My preferred method for you to submit it is your mix name, that is the name that is to the left of the @ sign, with a .1 and then .rmd. In other words, what I want is your mix name .1, meaning assignment 1, .rmd. Is that clear? And the next one obviously will be .2.
Do you want the HTML files too?
You might put it in, just in case I have trouble with the .omd. You might put the HTML file in there also, attach both of them. And I also want you to send it. Yanshin will be grading, so you need to send it to her and to me. That way we can correspond if she has questions. Okay, so make sure you send it to both of us. If you've already sent it, you might want to resend it with the HTML file too and send it in the correct format. I've received 3 or 4, so it's not going to be a big deal. Most people have said like assignment 1 with their full name, and that's okay. I was just, but again, I think it would be a good idea to have the date. I had meant to send out a email, and I spent all my time trying to get this lecture and the other lecture done, and I didn't get the email out. So that's why I'm saying if you don't get it in today, that's okay, but you definitely have to get it in by Friday. Yes?
When will the second assignment be due?
It's going to be a little quicker. This first one I sort of stretched it out because actually 10 will be coming up before too long. So I don't know. I'll probably give a little bit more. It's going to get contracted as we go along. It probably won't be at the end of next week. It may be the following week. Again, I'm sort of going slow to get you started, and as you get more accustomed to R, then they'll be a little more frequent. But again, there aren't that many assignments. I'm probably in Chapter 12. I'm going to split it up into 2 assignments because it's a very long assignment. So, any other questions? Okay. I guess at this point, what I'm planning to do today is finish Chapter 10. I'm also going to show you how to do what we're doing in Chapter 10 using jump. The other section of this does use jump, and you'll probably see why. You'll see the pluses and minuses of jump. The minus is you get what you get, and the other big minus is you can't do reproducible research very easily. So if you're doing a thesis, there's a strong reason why you want to do it in a reproducible way. So now I'm going to go into Studio. By the way, I'm having some issue with that router in there, which is why I haven't been using this. And in particular, since I upgraded to iOS 7, there's kind of a workaround I have to do on my settings. So I will hopefully do that tomorrow. I talked to some of the network people, and I'm going to try to get that set up tomorrow so I can use it again. But So in the meantime, I'm going to, again, I'm sort of editing this book, so I can bring up a version of the book on certain topics, which you can follow along in your book. So this is chapter 10. Now, what's online is, what I have here is slightly updated. But I may update it some more. I will be updating what's on the website. There are a few things I have that I'm going to show you today that are not on the site. But again, I'm going to be adding a few more things, and then I'll repost it. So I'm going to go in and knit this first of all, so we can take a look at it and get some sense of where we are. We were talking about the Saul's example, and I'm going to actually need to execute some of this code before I do too much. We did the one-way analysis of variance, and we used the LM function to do that. And then we talked about multiple comparisons, and we used the pairwise.t-test. And later today, I'm going to be using the pairwise t-test to do other things that go beyond Fisher's LSD. In Fisher's LSD, it's okay to have unequal sample sizes. Now, student Newman-Coles and Tukey's, basically they want an equal sample size, but if the sample sizes are not too unequal, you can use the harmonic mean in place of it. And by the way, apparently, I was thinking that there should be a 2 in front of the mean square here and here, but that's actually not the case. I think they've integrated that into the Q value, but at any rate. I would describe, well, if you look at the book, you'll also see there's Duncan's new multiple range test is discussed. To some degree, I would define Duncan's new multiple range test as kind of a legacy approach. That is to say, it's not used very much anymore. It used to be used a lot. And that's probably true of student Newman-Coles also. And actually, it's probably true of Tukey's, even though Jump, for example, has Tukey's in it, as I'll show you. But more importantly, there are some more modern methods, which I'll get to in the last section of this chapter, that I think are increasingly being used. Chaffee's method is one of the ones you can use, and it can have unequal sample size. It's one of the methods you can use to do any types of contrast. You can do as many as you want. You're protected in a family-wise sense. The problem is that the intervals are so wide, you usually don't find much. So, yeah, it's kind of one of those ones where you can sort of explore to your heart's content. But you're only going to find the really big differences. You're not going to find sort of marginal ones. Now, what I'd like to do is I'd like to talk about this, and that is the 1 degree of freedom comparisons. And I'm going to show you both the book, which has an example of computing this, and then we're going to go, at this point I'm going to go into Jump and show you how you do it in Jump. You actually can do these, in Jump, but when you're doing orthogonal contrast, we define those in such a way that we're taking linear combinations of the means. In this case, we have 2 linear combinations, L and M, so that's, and again, the A1s and A2s, I'll show you how you construct those. I'll show you in the text, and then I'll show you how you construct them. The A's and B's are selected not only such the sum of the A sub i's equals 0 and the sum of the B sub i's equals 0. We do that in order to be a contrast. In other words, to be a contrast, we need the sums to be 0. But if we want them to be orthogonal, then we also have the sum of the cross products is 0, the sum of A sub I, B sub I is 0. And what we can do is take the sum of squares due to the treatment effect, and we can actually break it up into A minus 1 orthogonal contrast in a number of different ways. And so I'll show you how that's done. This is sort of the computing formulas. And what I believe I'll do at this point is I'm going to show you how to do this in terms of the book. By the way, for those of you that know Unix, this is a make file, and that actually constructs the book from the raw text files to the actual production book, and it does it very efficiently. In other words, I have a whole bunch of files, and if I've only changed certain ones of those, it only actually has to redo those. And so that looks rather cryptic, but if you actually see how powerful it is, without that, it would be much harder to produce this book. This is called a Unix makefile. At any rate, so we'll take a look. Take a look at the. We'll take a look at the book. I'll put it on a continuous scroll, otherwise it's too small. And I'm going to go into, I'm going to go into chapter 10, and I'm going to look here. So I'm going to look at an example. Now, unfortunately, what you see here is sort of typical of the way books used to be written. And by that I mean they don't give you the raw data. They give you summaries, and then you compute more summaries from the summaries. So they are, in other words, this book gives you the totals, for example. And if you actually look at the formula, look at the formula here, you can see that, we do need the totals. And so we can compute, if we have the T sub j's, which is the totals for, T sub j is the total for group J, and if you get all those totals, then you can take the sum of the C sub ij's, in other words, those contrast the C's or A's or B's or whatever. You can take the linear combinations of the total squared and divide by n times the sum of squares of those those contrast coefficients. So, you can compute them if you were doing it by hand, but if you don't have the raw data. So what I've actually decided to do is, if I know the totals, I know the means, or I can easily get the means. And actually, I know this is my estimate of sigma squared, this 0.86. So if I wanted to generate data, how would I do it? Well, I know I could use the sample means. I could use the sample means as the population means, and I could use the 0.86 as sigma squared, and then I could actually go in and randomly sample from a normal distribution with those means and the sigma squared for each one, and I could easily generate it. Now the problem is it's going to be different than this, and in fact every time I generate it, it's going to be different. But I could pick one that's close to that and then redo it. So you can kind of retrofit these if you want, and if you learn R programming, that's actually pretty easy to do. But I have to generate it such that, in this case, there are 5 groups, and I have to generate it so I have group 1 that has a normal distribution with a certain mean and a variance. The variance is 0.86, and group 2 would be generated with a different mean. In R, you can actually do this quite efficiently. It's pretty simple to do it. You might want to think about how you would do it. But in R, it's not hard to do this. At any rate, now let's suppose, so if I'm a researcher and I'm interested in these additives, and perhaps no additive to toothpaste, and I'm a researcher and I want to compare these additives, I may a priori, that is beforehand, I may have certain contrasts I'm interested in. I'm not just interested in, say, there's a difference between these 5 additives, and one of them is not an additive. I may have certain things. So for example, I may want to compare no additive to some sort of additive. That would compare 2 to the other 4, right? And then I could compare, like, I could do things like compare a whitener to fluoride. In fact, how many independent degrees, how many comparisons can I do that are independent of each other? Well, you can do as many as you have degrees of freedom, which is a minus 1, which is 4. So I could actually do 4 of these independent orthogonal contrasts. Now, generally speaking, orthogonal is sort of geometrically the same as the statistical concept of independence. It's not always quite true. But with normality, there tends to be, with normality, you tend to, when you're talking about things that are being orthogonal, that's equivalent to saying they're statistically independent. Now, if I compare treatment A to B and then A to C, are those two independent, statistically speaking? No, because they both involve A. So if I compare A to B as a contrast and A to C, those two contrasts are not independent because they both have the same part of the same data in them. They both have the same observations from A. So they're not orthogonal. So I can't, I can't overlap in that sense. And that's why that second condition, the sum of the A sub I, B sub I is equal 0, that cross products being 0 is what gives us the independence. Now what that means is we're going to take the sum of squares due to treatment and break it up into pieces that sum up to that total. So in other words, the sum of squares is going to be partitioned. So geometrically what we have is a 4-dimensional space, and we have this vector from our data, and we project on this space. But then we break the space up into 4 pieces in such a way that we can project independently. And so that's something that you might understand if you know a little bit of linear algebra. So, but again, I'm not going to focus on that. What I'm going to show you is, in fact, that the sum of squares we're going to get is going to sum up to the total sum of squares. Okay, so what comparisons might we want to do? Well, here are 4. We might want to compare I don't know if you can read that, but compare the additive, no additive. That means you're comparing mu2, or the second group, to the other 4. And then you might do whitener versus fluoride. Well, which ones are the whiteners? Well, that's 1 and 5, I think. What vice? Whiteners are 1 and 5, and then chlorine are 3 and 4. So this next one I'm comparing 1 and 5 to 3 and 4. Now notice, and I'll show you how to. I'll show you how, not this example, but I'll show you how you might do this in jump. And then the next one is comparing a whitener with the whitener and to the refreshener. So that's comparing 1 to 5. In other words, mu1 minus mu5 equals 0 is the same as saying mu1 equals mu5. And then I'm comparing fluoride to fluoride with freshener, which is 3 to 4. So those are 4 orthogonal contrast. Now, if you go through these hand calculations, if you have the totals and you go through these calculations right here, for each of these 4, what you end up with is if you take the sum of squares among two, you have the 4 degrees of freedom, that's A minus 1, and you have the sum of squares, which is 136.8. If you calculate the sum of squares for each of these, which we gave the formulas for, you'll see that the 4 add up to the 136.8. In other words, the 2.8 plus the 116.6 and so forth, they add up to the 138. That's why we say they're orthogonal. We have partitioned the sum of squares into 4 independent tests, and we can test those independently. Okay, and you can see that you can see that the F test at the 0.5 level for 2 out of the 4 of them are independent. These are the critical values that is given in the book. That's the actual 0.05 value in the upper tail. And you can see that the second and third contrast, notice the asterisk beside them, they are significant, but the first and fifth are not. Now notice that the overall test is highly significant, but that overall test is primarily due to the second and third contrast. The first and fourth contrast are actually not significant. Now it might be more informative to have the p-values, because then you can sort of see, well, how insignificant are they? Is it near 0.05? Okay. So I was thinking that they talked about the saw example, I thought. Yeah. Yeah, what they say, and this is a saw example, and we'll do this in jump. In a saw example, um, suppose A and D, these are four different saws, but suppose A and D are sort of home models. They're not professional, they're not work models or industrial models. Perhaps meaning that they're less expensive, the steel is, a little less quality in the steel and so forth. And so suppose then A and D correspond to home and B and C correspond to industrial. So if we compared A and D to B and C, and then we compare A to D and B to C. So we have the 3 degrees of freedom, that is, 4 treatments, A minus 1 is 3, and these are, in fact, you can show that the conditions for orthogonal contrast, that's what this shows, and then if these are actually my coefficients, here I'm getting A and D versus, notice the minus signs versus B and C, and here I have A versus D and B versus C. So those are my coefficients. And you can show that those coefficients, the sum of cross products of those coefficients, that's what they're showing here, that the sum of cross products of those coefficients are 0. So there's orthogonal contrast. Well, if you look at the pattern, you'll very quickly see that you don't even have to multiply it out. You can tell just by looking at them that they're going to be 0 because of the plus ones and minus ones, and things are going to cancel out. So then the question is how might we do this in jump? So I'm going to mount this, and now I'm going to open jump, and I just noticed that my license is about ready to expire. So hopefully by next Monday, I guess I'm going. Okay, I'm going to say open. I just want to show you one thing. I'm going to say open. And actually, see what I've done actually is if I go into Mozart, which is a server, I can go into my account and go into the same files that I'm using in RStudio. And I actually have in my notes for chapter 10, I actually have this text files. I've already saved it as a jump, but I want to show you. That's the text files. Notice that's what it looks like. It's got here's the model and the angle. And I don't want to read it in as text. What I'm going to say is, jump, try to open this with your best guess. Now notice that I have the variable names at top. And notice because I have A, B, C, Ds, those are in fact character. And so hopefully jump will be smart enough to know that that's going to be a factor and the other is going to be continuous. Now if I were to use 1, 2, 3, 4 for my solves, it would have thought, or it would think that in fact the model is numeric. Now you can change it, once you get it in, you can change it to a factor. But let's try the best guess, and let's see if we can open it, and we can. And so there is the data table in jump. Now there are 2 ways you can do this, and I'm just sort of showing you sort of the way the other section may do this. There are 2 ways you can do this. I can go in and analyze and say fit y by x. And so what I want to do is make angle the response, and then the model is the x. And that's all I have to do. And that's basically equivalent in R to saying y tilde x, or in this case, angle tilde model with the LM function. So then I say OK, and well, I get a graph. So that's nice, but it's not all I want. So we have these little drop-down menus, and I can do means ANOVA, so I can do the ANOVA test. And so what does it give you as sort of standard output? Well, it gives you the sums of squares, the mean squares, and the f-test. Do you remember that 0.038 it's not, oh yeah, it's giving the mean square, yeah. What is it? This is the same. I'm just trying to see why these appear to be different. I assume they're adjusted, but the the 356. Yeah, that's the same. Why is this ratio different? Is it different?
It's not different.
360 and 101. Yeah, it's the same. Yeah, it's all the same. Oh, the only difference is they're giving this total down here. That's the correct, what do you call it? Corrected total sum of squares, which will be the sum of the two above it. In other words, the 19 degrees of freedom is what's called the corrected total, and actually the book does this too. And if you look at the corrected total, simply the sum of the model and error terms. So those two add together in terms of the sum of squares. So in other words, the sum of these two give you this bottom one, and then I'm dividing by the degrees of freedom to get here. I take the ratio to get the f-test, and so we're getting the same results. And then these are the means, and they're giving confidence intervals on the means. Okay. The way they do multiple comparisons, so if I look at compare means, then I can do the student t's, which is Tukey's, and this is kind of interactive. Again, it's not the greatest thing if you're trying to put it in a report, because in order to find out what's different, if I select A, then the reds are not different, and so A, B, and C are not different, but D is different. In other words, if I compare A and C are different, and you can see the letters, again, the A, that says A and C are different. Now, on the other hand, if I click D, you'll see that A and D are different. And in fact, that was the same thing we got. That was the same thing we got when we did the multiple comparisons. If you go back and look, when you go back and look at, whoops, where did we do multiple comparisons? When we did Fisher's, then we found that that's C and that's A and C, and then C and D. Is that what we're getting? Let's try this. I need to look at that. Doesn't seem to be quite the same. I was thinking we had the same thing, that C and D were different. A and D are different. A and D. I need to sort of see how they're computing this. Let me look at that a little bit more. If you look in at the comparisons, you can also do Tukey's. And again, you're going to find fewer things significant there. In fact, you don't find anything significant there. No matter how you click, nothing is different. That actually conforms to what we did, because what we did was with Tukey, I don't think any of us, yeah, none of them were completely to the left or the right of 0, although C and D were very close. If I look back at jump, then if I look at this is, I think it should light. That's D, I think, and then this one is C. So the top circle and the bottom circle, basically, I think the idea with jump, if the circles don't intersect, they're different. I think this is the way it's working. I need to sort of read that a little bit, but I think if the circles don't intersect, then they're different. Okay. There is, by the way, there's a help, and in fact, you can sort of bring up a complete, I'll look in there to see exactly how to interpret that, but in jump, there's basically a whole book here that tells you how to use jump, and it tells you, has lots of examples. So, okay, so we have this basic type of analysis here. And by the way, here, I guess, here's the LSD, and this is sort of another way of representing it, saying this is ordered. I see. Okay, the order is different. That was the issue. Is when I was looking at them, the order is different. You have C, B, A, D, and so the AA means B and C are not different. And then the BBB means B, A, and D are not different. Okay, so that's Fisher's LSD, and then this gives the confidence limits. And again, the question is which ones, the lower and the upper, which ones include 0. So C and D do not include 0, nor do A and C, but all the others do. That's actually similar to the way the HSD does it. And here are the HSD results down here. So if you're doing it in jump, this is the way you can do multiple comparisons. Now suppose you wanted to construct these orthogonal contrast with this data, and that was what comparing A and D with B and C, and then A and D and B and C. So how would you do that? Well, you can't do it here. You have to run another model. So this model I'm going to run is similar to the LM model. In other words, what I did initially is I went in and I simply do a y by x. In other words, I'm doing a binary thing where I have one x and one y, and y is going to be the response and so forth. Now, this little graph is kind of neat in that it says, but if I have a histogram, and by the way, the green means it's an ordered histogram, so it's ordinal, whereas the red means it's based upon, both of these mean that the data is categorical. And this means, the green means it's ordered. Notice the ordered increase of the bars. So the green means it's ordered categorical, whereas in this case, the red means it's just categorical. And this smooth one means that it's continuous. So in other words, if I look at this cell, that says I have a continuous outcome, but I have a categorical x. So y is continuous. What that means is we're going to get a one-way analysis of variance. On the other hand, this one right here, that's chapter 10. This one right here says if the outcome is continuous and the predictor down here is continuous, then it's bivariate, it's a regression. If, on the other hand, both are categorical, which is this one, then you do a contingency table. Now, a contingency table isn't something I spent a lot of time on because that's something covered in 511, not 512. So if you don't know contingency tables, you can play around with a jump, or you can go back, I forget which chapter this is in. It's in one of the earlier chapters of the book. And this is a topic which is right at the end of this book. Logistic regression is where your predictor is, what you're trying to predict is either binary or categorical, and you're trying to predict it from a continuous variable. And in that case, you get what's called a logistic regression. It's a very common type of model. It's the type of model that we cover in Stat 555, although a lot more complex than just that simple example. So, and in fact, if you take that both the outcome and the predictors are categorical, we can extend that model to we have multiple predictors, some of which are categorical, some of which are continuous. So we can get into these types of models. So if I was trying to predict 5-year survival of cancer, either you survive or you don't, that's a binary outcome, right? So I'm trying to predict the 5-year survival rate. And in fact, what I'm trying to do is predict the probability that a person survives 5 years. But again, I'm trying to predict a binary outcome. I would use logistic regression to do that. Well, that may depend upon the nature of the x. Again, if x is categorical, then I would do something. I would do some generalization of contingency table test. But at any rate, this is fit y by x. But if I have a more complex model, I'm going to say fit model. Fit model so I'm going to pick y is again angle, but I'm going to put down as an effect model. Now, obviously, it looks like I could put lots of things down here, and that's in fact true. That when you get to more complex models, you're going to fill in more things as predictors. In this case, we only have one. We're trying to predict angle from the model. Or thinking about it another way, we're trying to figure out, do the models differ? So I'm going to do what's called a standard least squares. I'm going to run that, and when I do, I get something like this. Now, I get this same analysis variance table I got before, right? And then I have this residual. Here I get the residual. This is one of the diagnostics. I have the residuals versus the predicted. That's one of the diagnostics we talked about. And so this is something we can look at to sort of see if, in fact, the residuals are somewhat evenly distributed around 0. So at any rate, so I get these types of things, and there are other things that you could get. You can save certain results and so forth. But what I'm interested in is in a model. And a model lets me do things like, here I can do, this is similar to what we had before, I can do the A, B, C, D, and I can get, these are the least squares means, and I can get these student t differences, which is Fisher's OSD, and I can get, again, this and this are going to, A versus B and B versus A are going to be the same. So, at any rate, the signs are going to differ, of course. But these are the effects of interest. If I look at this column or this column, those are the effects of interest. And what I'm going to do, so this sort of gives me a comparison. That's the same thing we looked at before. Those are the means, and those are the mean differences. What I'm interested in now is if I go, and I can also do Tukey's here. Dunnett's is a multiple comparison procedure where I compare everything to a control. Suppose you have a control and then you have one or more treatments, and you want to know how do those treatments compare to the control. So you may have a control drug, and then you have other drugs you've developed. You want to know how each of those compares to control. So what you're comparing is a control to each of the treatments. That's what's Dunnett's is optimized for that type of comparison. But how would you do a more general thing? Well, I can specify a contrast. So we had an example, and let's suppose I want to compare A and B versus C and D. How would I do that? Well, what I'm going to do is click on a plus I'm going to click on a plus with A and D, and then I'm going to click on a minus with C and D. Now what that does, I have a plus 5 with A and C versus a minus 5. So that's one of my contrasts. So if you compare that to the book, you can see that's exactly what happened here, right? I've just reproduced that. And then if I go in and I say, okay, next, I want to compare A versus D, so I can get a new column here, and I can do A versus D. So a plus and a minus. So I get a 1 and a minus 1. So again, now I now have the 1 and minus 1. Okay, let's do one more column. And what I'm interested in here now is B versus C. So I can go in and I can do this. Okay, and then let's say we're done. So now, oh, it didn't break it out. Parameter functions. Let's see if this gives it. I didn't want the 3 together, although this illustrates the fact that, well, it illustrates that the sum of squares is in fact total. I was thinking it would give you the individual ones, which is what I wanted. So let me go back and just do one more. Hopefully it will. I'm going to remove this. Okay, now I'm going to go back and do them one at a time. This is kind of a nuisance. I'm going to go back and do it one at a time. So what did I have? A and D versus B and C. Whoops, 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 whoops. That was not correct. I need to remove that. I meant to hit the minus sign for 2 of those. So what I want is A and D versus B and C. Okay, so let's just do it. So I have a sum of squares of 980 with 1 degree of freedom versus 16 in the denominator. The F is 9.67 and the p-value is 0.0067. So I don't recall that was, let's see what. So he doesn't give the results. Interesting. Let's assume it would have been the same. The results aren't in the book for this. He gives the results for the toothpaste, where there is no data. So, okay. So it appears that I'm out doing one at a time in order to get the individual degrees of freedom. I was hoping that it would give, when I did each one of them, I was hoping it would give the individual ones. And so that's not quite as nice as I would like, but you can do it, of course. So one of the things, of course, that you do is when you don't know an answer to something, you do something like that. And then you see if anyone is doing orthogonal contrast in R. And in particular, you want to know whether or not you can. It wouldn't be hard to write, a function that does this. But you always kind of say, well, does someone else do it first? And so, and in particular, what you're looking at is for a package. You're not just looking for someone's, little interactive session where they do this. You're looking for a package because that makes it nicer. But okay. So at any rate, I'll look a little more. It's hard for me to believe that someone hasn't done this in some sort of package. But I'll look at it. If not, again, as I said, it wouldn't be too hard to write a function. But ideally, what you would like is that it would be in a particular package. So, there's actually a package, I think, in R that There is a package called AOV, and this is a simpler package than LM, but it also doesn't do as much. And I'll mention that I haven't been using this because as we get to more complex models, this isn't going to cut it. I believe that this package, this function AOV, as I recall, this does say a list of contrasts to be used. Now what I need, and if that's true, then we could do it here. But as I recall also, this is the little bugaboo here. AOV is designed for balanced designs. And so if the n sub i's are not the same, you may have difficulties here. And it says, and the results may be hard to interpret without balance. And that's why I haven't put the focus on. So for a number of the examples in the book, we could use this AOV because a lot of the examples in the book are balanced. But in general, the LM is better. It's much more flexible. But it does appear that you might be able to do some contrasts in here. So I'll look into this. I mean, that Sol example is balanced. So the question might be that if it's not balanced, then again, it's sort of like using the harmonic mean within Tukey's and Sydenham and Coles. If the degree of balance is slight, that is, if the n sub i's are not too different, then I think this is approximately correct, and it's probably okay for the most part. But again, this is why I haven't put the focus on this particular function. But it does appear you can do contrast here. So I may use the AOV just to illustrate it, and if I can do contrast, then that yeah, okay. I'll look into this a little bit more. So it looks like we can do it here. The question is there a more general way of doing this? The issue with orthogonal contrast with unbalanced data, there's issues that arise there at any rate. So. Okay, so any questions? That's how you use jump. Okay, and so I've used two different things in jump. If I have a single x, I can use this. If I have more than one x, I can use fit model. Fit model is sort of the equivalent of LM. I guess I would say it this way, that fit y by x is sort of the equivalent of AOV, but AOV, well, not quite, because AOV, I believe the fit y by x is okay even if the n's aren't equal, whereas AOV once the n's equal. But again, the fit model is somewhat equivalent to the LM in R. You can think of it that way. So I tend to use the fit model because I think you can do just about everything in it, plus additional things. Now, one of the things you can get are the parameter estimates, and if you in fact look at this, I'm going to come back to that in just a minute. Can anyone tell me from that what the constraint is? Now the book says the sum of the alpha sub i's equals 0. What does R say? I'm going to show you why you have to have a constraint in more detail in a few minutes. But the book has the sum of the alpha sub i's equals 0. That's sort of the classical way of doing it. Jump says, I'm going to set the first level alpha 1 equals 0. What do you think that's doing?
For R, the alpha 4.
Yeah, see, there is no D. So jump is setting alpha 4 to 0. It's setting the last one to 0. You'd think there could be some agreement. And I think that, I'm trying to remember what SAS does. SAS may do the sum of the alpha psi equals 0, but I need to check that out with some SAS code. I'll check that out. In fact, I'll show you how to run this in SAS, just so you have the full experience. That's not the full experience, but get RSAS and jump, you've covered a lot of territory. So I'll probably show you the R code. I'll show you the SAS code for running this also, and then you can see what the constraints are. I think that SAS has a proc GLM, which is confusing. That's sort of like R's LM function. R has a GLM function, but GLM and R mean something different than GLM and SAS. So you got to kind of keep all this stuff together. Here's the distinction. GLM in SAS means general linear model. GLM in R means generalized linear model. Generalized linear models means that I can fit things like Poisson models, binomial models, et cetera, et cetera. General linear model is still normal models. If you're going to do Poisson models in SAS, you use something different. So the GLM for general linear model, that was one of the original things in SAS that was developed way back about 1970. So maybe they hold the rights to that, but everyone now uses GLM to mean generalized linear model. So, at any rate, well, let me come back to this in just a second. So let's go back here and let's go back here and take a look. I want to talk about estimation a minute. And last time I did talk about some of this, and the thing you're most interested are the last two. Contrasting the means, mu sub I minus mu sub j, you're looking at comparing pairwise every mean to every other mean, let's say. And then that standard error is, that's the mean square error. If I took that outside the radical by taking the square root, then that's what I call S sub p, the pooled estimate of the standard deviation. That estimates sigma hat, whereas the MSE estimates sigma hat squared. Now remember, our basic model said that the epsilons, that is the error terms, are distributed normally if a mean is 0 and a variance of sigma squared. And that variance did not depend on the group. In other words, the variance sigma squared was the same for all groups. And in fact, if it appears that the variance for some of the groups are bigger, then you've violated an assumption. And then the last one are the contrast. So if I want the sum of the a sub I mu sub I, that's contrast. If you assume that the sum of the a sub I equals 0. And so if I can estimate that simply as the sum of the a sub I y bar sub i's, that's the estimate of the sum of the a sub I mu sub i's. Now I hope by this time you understand the difference between mu sub I and y bar sub I. Mu sub I is a population characteristic. You don't know it. It's a parameter. A parameter is some characteristic of the population. And you're trying to make inferences about those parameters. In this case, we're trying to make inferences about the mu sub i's, and do they differ? Y bar sub I are statistics. They're random. If I get a sample, I get a set of statistics. I get a set of means. If I get another sample, they're not the same because of the random error. So the y bar sub i's are the statistics which estimate the parameters in this case. And we see this, that is what's called the estimated standard error. I have standard error, but technically it's the estimated standard error because I'm actually estimating the sigma squared. Now we put on this constraint, and when we ran this, notice that we got 39. Oh, wait a minute. No, they're using the sum of the alpha sub I equals 0 because that's what they're getting. So jump is, in fact, doing it the same way. They're using the sum of the alpha sub I equals 0 is what they're doing. These are exactly the same as this. So they are using the sum of the alpha sub I equals 0, which is fine. Now, in order to do that, that is not the default in R. I had to put contrast equals, and then I used a contrast.sum to get that. Now, I should mention that I put it here, and I have to put it every time I do it, but there is a global option. So I could define, not only could I define this globally, but I can save it so that every time I do analysis of variance, it uses that contrast. So in R, it's not, it's not so much that you're stuck with changing it every time I have a model. You can save it globally. So now that so again, these are the same, and these parameter estimates give the standard errors, which are basically within rounding error the same, and then they give the t-values, which are the same, and then the p-values. So in other words, this is what JMP gives you. Now, I've created an object. I've created an object called fit.solves, and fit.solves was back up here. And when I ran fit.solves, that was simply the model. Did I rerun it? I guess I reran it. Yeah. Well, I must have rerun it up above with that. Where did I run it? Yeah, right here. Okay. So maybe I better go in and run a few of these. Let's go back up and see if we can find this. So I'm going to read, whoops. I'm going to read this. I'm going to execute this. I don't know if I set the working directory correct, so I'm going to do that and look at the space. Yeah, I'm okay. So I'm going to create I'm going to run fit.solves using that reads it in, and then I'm going to skip down. I've done all this, and here I'm going to run this with the sum contrast. I'm going to run that. Oh, what happened? I'm going to open the connection. Oh.
You're still in your root directory.
Yeah, I had never gotten into here. Okay, this should do it. Now let me set the directory again. Set this as working directory. Okay. So now I need to go back up here, unfortunately, and read that in again. And this should run now. And then I'm going to go down and do the model. Maybe I better attach it. So I'm going to attach it, and then I'll go down and do the model. Okay. So now I should be able to, well, this is the ANOVA. That's just the overall model. Let's go down. All the comparisons. Estimation. Okay. So I have this fit.solves. I'm going to create a summary. And so the AOV table just gives you the overall table where you have the treatment of 3 degrees of freedom. In this case, it's model. And that gives the analysis of variance table. If I want to break it down into these, if I want to break up the 3 degrees of freedom of a model down into the particular contrast, and based on the sum of the alpha sub I equals 0, then I have to use summary. So by doing summary, and I actually save this into an object called sum solves. So I have two things. I have fit solves and sum solves. The fit solves is for the fitted models. The sum solves is for the summary. And if you actually look at the output, I keep forgetting it's here. If you actually look at the output, again going down here, fit solves has these attributes. So if I want to get, if I want to get certain things out of it, like the coefficients, I can actually extract coefficients from that object. But if I want to extract other objects like the estimate of sigma hat, I have to get it out of the sum solve. So this is an estimate right here. This will pull out the estimate of sigma hat. Whereas if I want the coefficients, I would have to do it here. Now I don't need to totally, I can use the dollar sign to extract it from the object. So I could say fit solves dollar sign COEF. As long as it's unique, I don't have to have an exact match. If I have enough characters, it makes it unique. So I can abbreviate COEF because there are no other terms here that start with COEF. So I don't have to print out, I don't have to type out the whole thing coefficients. So so here are the model means which I computed for. And then if I say fit solves dollar sign coefficients, these are the coefficients. Now these coefficients are exactly the same as these values up here. Okay, so I extracted that first column right here, the estimates. Those are the coefficients. Now, if you look back, you might ask, well, how did I get these standard errors right here, and how did I get these? How did I get the t-values, for example? How did I get this part of the table for the model 1, 2, and 3? Okay, this is estimating alpha 1, alpha 2, and alpha 3, right? So in other words, model 1 is actually estimating alpha 1. So that value of minus 6 is alpha hat 1, and then model 2 is alpha hat 2, and then 10 is the alpha hat 3. And so if you go back up here and kind of look at things and you say, well, how do I get the standard error of that? And the way you get the standard error is to take the mean square error, and then you multiply that's sigma hat squared, which you derive from the sum fits, the sum solves dollar sign sig. That gives me sigma hat. If I square it, I get sigma hat squared, which is the mean square error. And then I'm going to multiply that in the numerator by capital N, the total sample size, minus the n sub I. In our case, all of the n sub i's are 5, so that would be 20 minus 5, it would be 15, divided by the n sub I times capital N, which is 5 times 20, or 100. So where did I get? So if I go down and look at my R code, I say, okay, I brought this outside of the radical. In other words, inside the radical, I need the mean square error. But if I take it outside of the radical, then it's just sigma hats without the square. Okay. But I'm going to leave this part inside the radical. So if you look at my code right here, I'm taking sum solves sigma. That is sigma hat. If I square it, it's a mean square error. And then I'm going to take the square root of the 15 over 20. Now, since my sample sizes are the same, they're all the square root of 15 over 20 for each of the groups. So now what I'm going to do is I'm going to take the coefficients, and what does a minus 1 mean? It means I don't want the first one. I don't want the one that's mu. I just want the alpha 1, alpha 2, and alpha 3. In other words, the coefficients are 4 of them, right? The minus 1 says don't include that. So in other words, I don't want this one. I want these 3. What I'm trying to get are these standard error, the 3.9s. That's what I'm trying to get. So if I now take these coefficients without the first one and divide by the fit standard error, which is this one, and by the way, what is that? That's 3.897? What is that? That's these, rounded off. And when I divide it, I'm going to get these 3. So how did I get those 3? I got those 3 by dividing the coefficients by this 3.997. 897 or 90. And then these are my t-values, and those correspond to these three numbers right here. So, if you compare this to jump, you get the same thing. But now maybe you understand a little bit more about how you compute these. In other words, how do you compute those standard errors? I just showed you, both algebraically, which is this, and numerically in R, which is this, right here. Now, you might ask, I keep talking about, time flies. Not going to quite make it this time. I keep talking about these constraints. Why do you need a constraint? Suppose I would have, if you look here, suppose I would have had all zeros here, and then I'd have another column, model 4, that would have all zeros except it would have ones down here. Do you understand what I'm saying? In other words, you see how this first one, this is mu plus alpha 1. That's the first observation. And then this is mu plus alpha 1, 2. That's the second observation in the first group. And then here I have, this corresponds to mu. This is mu plus alpha 2. That's the second group. And then the third group is mu plus alpha 3. Now suppose I would have had a fourth column, and suppose all of these would have been 0, but the fourth column would have had all zeros except it would have ones down here for the last group. Then you would have mu plus alpha 4, right? But I claim there's a problem. And here's the problem. If I would have all zeros and then ones here, and then I'd have zeros here, I claim that these last four columns would sum up to the first. In other words, if I sum 1 plus 0, it's 1. And that's what's happening here, right? Here I'm summing 0 plus 1 plus 0, and those are 1s, like this. And here I have 0 plus 0 plus 1, and that's what so I get a 1 here. If the last one was 0 plus 0 plus 0 plus 1, that would also sum up to these 1s. So the last three columns would then sum up to the first one. That is a collinearity. That says that one of my x columns sums up to the other columns. That is what we call a collinearity. Now, this can happen in regression. Suppose that I'm doing a regression model, and I have a midterm, and I have a final, and I have a total. And I'm trying to predict something from those scores. If I have a midterm and a final and a total, the first two sum to the last. If you try to fit the regression, it will blow up. It won't work, because you have a collinearity. We also call it a singularity. And so I have to put a constraint on it to get rid of that singularity. I don't care what the constraint is. I just have to reduce the dimensionality from 4 down to 3 in those last columns. So the sum of the alpha sub i's, if I have the sum of the alpha sub i's equals 0, that says alpha 4 equals what? It equals minus alpha 1, minus alpha 2, minus alpha 3, right? That's where you get these minuses. That's why these minus 1s. Because what you're saying is that the fourth group is mu minus alpha 1, minus alpha 2, minus alpha 3. But because of this constraint, that's the same as mu plus alpha 4. Okay, so this is called the model matrix. And in an R, we can get the model matrix by that function, model.matrix. Now, suppose, and I'm going to stop after this, suppose I'm going to print out now the model, which is, notice it gives 1, 2, 3, 4. And R has what are called levels, which are A, B, C, D, and it has formal levels. Formal levels replace the A, B, C, D by numbers, 1, 2, 3, 4. And then the next one is the Y column. Now what I'm claiming is that the third column, here's what I'm doing, and I'm sort of gradually teaching you a little R. I'm taking the model sols. The model sols is this. So I'm taking this matrix and I'm multiplying it times this vector. So I'm going to talk about that a little bit more, about what matrix multiplication is. But basically, this one gets multiplied by the first column, this by the second, this by the third, and this by the fourth. And then you add them up. And here you get these, which are the predicted means. In other words, those are the means, which are 33, 43, 49, and 31. And then the last column are the residuals. Notice that I have the residuals. And how do I get the residuals? I can get that from Fitzsall's dollar sign residuals. Again, up here, if I look, I see that the residuals are right here, so I can get Fitzsall's dollar sign residuals. So that's residuals. I could also get the predicted values right here. I wouldn't have to compute them. I simply did it to show you, but these are the y-hats right here. And that's the same as this. That's the same as this third column here. These are the y-hats. So I wouldn't have had to do it, but I did it just to illustrate how you compute it. And then if you look below, and we'll go into that next time, this is what R does. It puts a different constraint. It simply sets all of these to 0, so this 1 actually represents mu1 because it's the first group. Because it's 0, 0, 0 for the last 3 columns. So mu sub A, or mu1, is in fact that intercept term. And then the next one is mu2, so that's if I look at the 1 and the 1, that's going to give me model 2 or mu2 and mu hat 2 and so forth. So we'll look at this a little bit more. What you're going to notice is when I compute these from R's restriction or constraint, they're exactly the same as here. In other words, my tests are the same. Now, obviously, the tests for those individual coefficients are different because they represent different things, but the overall f-test is the same, the predicted values are the same, the residuals are the same. The only thing that's different are the estimates of the alphas and the standard errors of those estimates because they're done differently. Okay, so I'll come back to that a little bit more, and I want to show you a little bit in R how you do matrix multiplication. And then when you get into something like this, in particular when you start looking at, well, how can we do multiple comparisons in a more modern way, then that's what we'll talk about here. For example, in bioinformatics, you get into a problem where you have tons and tons of multiple comparisons, and we need a reasonable way to control the error rate. We don't want it too strict, we don't want it too soft, we want something in the middle. And so we have these modern techniques which are in R, but unfortunately they're not in JUMP. And so this is where you get into why you might want to use R as opposed to JUMP, because if you can't do it, you write some code to do it, but most of it's there. Okay, so we'll stop there. So we're going to continue here, but I am going to start next time. It won't take us this long to finish. I am going to start next time, the next chapter, 11, so you start reading it. And I'll be sometime between now and Monday, I'm going to be posting the notes for that, and at some point I'm going to post the chapter 10 assignment, for those of you that are working ahead. Okay. So when you download the notes, you're getting all the R code, so you can sort of play with it. I recommend you do that. I may put in some R code for this section on 1 degree of freedom. I'm going to take a look at that. And then I'll repost these notes. So again, if you can get them in today, fine. Otherwise, Friday. I'm going to send out an email on this, particularly for the distance-based students who are working along with this. I'm going to send out an email, and I definitely want them by Friday, though. Any questions? Okay.